the podcast, Dr. Jihan Liu. And probably before we begin more talking about DeepSphere and AI, could you just please introduce yourself first?
Sure. So I'm Jehan. I am a senior lecturer at the University of Melbourne. My specialization is this AI subfield called natural language processing, also called NLP. And when I started this, this research in this topic, it wasn't a big thing like it is nowadays. It was really just me really being interested in trying to understand how we can build computational models to understand language. And that all traced back into my childhood. I was really into Transformers, the robot Transformers, the cartoons, and it always fascinated me how robots can talk and behave and speak like person. And so fast forward when I was at university doing a subject called machine learning, that's where I realized, maybe through machine learning models we can build potentially these sort of more like computational models that can understand human languages, and so that got me into NLP.
And has like the machine learning subject at University of Melbourne kind of evolved through these years? Because I think it's been, well, having looked at your profile, I think it's been like 10-ish, 15-ish years since.
I did my university 20 years ago, first year 2005. So 20 years ago. Back then there was no like all this divisions of machine learning. Like now you have natural language processing, you have computer vision. Back then in my days, there's just machine learning. It's only one subject. And you learn a little bit of NLP and computer vision stuff in that subject. Actually, not any computer vision. It's just machine learning and then a little bit of NLP. And that's about it.
And NLP has also kind of evolved a lot. There's been like subcategories within NLP. So, actually, it's kind of spun off with like the image generation. It's kind of been a lot there with like Sora 2, so that's video generation actually, and then Midjourney. And how does that really differ from what NLP has done, text generation?
Yeah. So NLP always has a lot of subfields, within itself. But just like any other research field, it evolves over time. Because as research matures in one area, and people move on to new areas to explore, right? To give you some example, back in my days, we don't do too much text generation, partly because text generation is a very difficult problem. The main text generation sort of subfield within NLP is machine translation. That's an active field since World War, basically in the 50s, where people are interested to translate Russian to English. So machine translation has always been very active, but that's only really the area that does a lot of generation. There hasn't been a lot of like summarization, all sorts of generation problem isn't really something that's super active because it's just really hard. When I was in my PhD, I was looking into topic class, this topic model, a particular model that sort of tries to learn topics, semantic topics from documents. Again, people don't do that a lot nowadays. Before my time in NLP, the biggest area is actually about syntax, learning how you extract verbs and nouns, etc. from sentences, trying to understand these sort of syntactic structures. That's actually what was the biggest thing when NLP, like 10, 20 years before I started. But now, complete change, right? Now, a lot of NLP is dominated by large language models, like ChatGPT. People explore all sorts of ways how you can use large language model for all sorts of text analyzing or generation applications. So it's evolved, a lot, but that's normal.
Would you say there's like any point in creating specialized models? It's like large language models are very good at general tasks, but so one of your past papers was DeepSphere. DeepSphere was more of a specific task to solve a specific problem. Is there any need to create those things anymore?
Yeah, so before I answer your question, just to give a bit more context, you're absolutely right. Your observation that now we move into this single model that does everything is actually really different from what NLP has been. Back in the days, prior to 2020, we built domain-specific, application-specific models. So you don't have a single model that you use and then try to do all sorts of things, right? Poetry generation, we build a specific poetry generator to do poetry generation. If you want to do machine translation, you build a machine translation model. If you want to do topic classification, you build a topic classification model. So, and that has been like that for decades and decades. And sort of that changed around 2020 when we start to see models like GPT-1, GPT-2, BERT, these sort of transformer-based models, where we realize you can pre-train these sort of transform models on just very simple word prediction tasks and train on lots of data. And it turns out they're a great generalist model. You no longer need to really just train a domain or application specific model, but you can take these sort of like bigger sort of like generalist model and then just use them and fine tune in some way to the task or application that you're interested in. And that was like that for like maybe 4 or 5 years. And then large language model came along, of course, and they are effectively scaled up version, even larger versions of models like GPT-1, GPT-2, or BERT. GPT-3 was at the time the largest model when it was released. And it has even new capabilities. You don't even need to fine tune them on your application anymore. You can literally just say, can you do this? And can you generate poetry of this style? And so again, that changed the landscape of things a little bit. But that said, coming back to answering your question, do we still need to build application-specific models? It sort of depends on the application, depends on the domain. In domains that I've experienced with, like I work with like a non-profit legal organization, for example, that tries to connect help seekers with pro bono lawyers. So that domain is sort of the legal law domain, for example, right? You can use ChatGPT to do things, but they're not super good because it doesn't really have the sort of the legal knowledge, particularly Australian legal knowledge that we needed to have, right? And so these are more niche sort of domains. You would probably still need to build application or domain-specific models because the generalist models simply don't have that sort of these sort of niche domain knowledge. But in many applications nowadays you don't. If you wanted to just build a summarizer for an article for news, you don't really need to do any domain-specific tuning anymore. Off the shelf, these large language models, they're very good. Just with the right prompting, they would probably do the job. So it kind of depends on the application, depends on the domain.
Yeah, and especially with the GPT series, I believe it's also possible to have your own data and then kind of fine tune a GPT model. So would that be, though I think with GPT models such as above 2, it's not really available to use for research purposes, is that true?
No, you can still use it for research for sure. Even GPT-4, even GPT-5, you're right. If you have like some sort of domain, like let's say we use the same example, the law domain, for example. If you have a big legal corpus, you can definitely fine tune the model, like continue train the generalist model into the law domain itself. And then after you fine tune, then of course it would be a little bit better than the generalist model in terms of understanding sort of the domain knowledge, the domain concepts, etc., etc. And that's a very standard way of doing this on domain adaptation. Yeah.
And kind of building from that, especially with DeepSphere, so I'll try and link back to poetry generation and things with that. So poetry generation was DeepSphere in particular was a language model that was really built for poetry generation. It was built on the Gutenberg corpus.
Specifically for sonnet generation, not any poetry to specifically only sonnets.
And I think sonnets, if you were to define them, I think there's a word that was brought up a lot, which was a quatrain, which was a stanza of 4 lines.
Yep.
And usually there's some rhyme.
Yeah,
so
there's some rules to it. Yeah.
AAB, AABB, I should say, AB, AB.
There are variations, yeah.
Variations like that. And I just want to know, especially with making these very specific models, if you have around, so I believe the model that DeepSeek was trained on was 3,400 sonnets. Tiny. So really, if you scale this model and you tried to make it more like a large language model, would it have been possible to trick professors that were trained in poetry?
So first of all, you can't just scale it up in terms of putting more neurons or more model parameters in it, because with 3,000 sonnets that we have, it would just overfit it, right? So you have to understand the model size and the data size come hand in hand. If you have lots of data, then you can train a large model. But if you don't have a lot of data, you can't actually train a large model, because then it will just memorize the poems and it will generalize. So we can't really just scale it up like that. If you want to scale it up, you would also need to now think, how do we increase the data size, right? And so you would probably need to move away from just sonnets. You would take in all forms of poetry, right, that you can find on the web, and then train, like, say, a more generalist poetry sort of model. You absolutely can train a large language, large poetry model. If you found billions and billions of tokens of poetry data on the web, you can, yes. But I guess it depends what you want to do, again, right? If your intention is just to create sonnets, do you really need to train such a large generalist model? I mean, it would be enough to use small data and small models to do the same thing, right? So it kind of depends what you want to do. But it's a yes and no to your question, because you need to get the right data size if you want to scale up your model size.
Yeah, and thinking back, so that's the thing you said about, do we really need to create a sonnet generating model? And when I was doing my research, I was kind of thinking, in poetry, it is a very niche topic. It's like not many people nowadays really do poetry, but there is like a cult following of poetry. But I was thinking, there's kind of this discussion at the end goal of AI, which is artificial general intelligence. I was thinking, in your perspective of artificial general intelligence, would like deep, really meaningful poetry be part of it?
So to answer your question, I guess let's talk about why we went to do poetry generation. Why we look at poetry generation is really, again, trying to understand whether we can build computational models that exhibit creativity, basically. Because in most of the things that people work on in the NLP research space are not creative tasks, right? Like in generation, I talked about machine translation is a big field. Now, machine translation, not to say there's no creativity, but really is a very, very sort of like task-oriented sort of problem, right? Where you have a piece of sentence or a paragraph, and your goal is to translate as faithfully as you can into another language, right? Of course, there's some creativity, how much what's the word you want to use and all that you want to consider to translate as faithfully as you can, but still fluent in a new language, right? But most people wouldn't think machine translation is like creating a poetry or drawing a painting, right? It's a very different problem, right? And so when we started the problem, the thing that we were just curious is, could we get computational models to be creative? But what does creative means, right? Creative in our case means if a person reads some poetry, right? Creative means that after reading these poetry and get very inspired and all that, you can create a new poetry yourself that expresses whatever emotion or lived experience you have. And this poem that you create is different. It has a different set of words, emotions, everything compared to what you've read. That is creativity. The inverse, not being creative, means you would just plagiarize some of the lines here and then create something, right? So what we're interested is, can computational models do that? If they read 3,000 sonnets, can they create new sonnets, new content, new emotion that is not part of the training data? Because if they can't, then that means that these models are not really doing any generalization and have any creativity themselves, which sucks for us, of course, because what we want to see is, do they exhibit creativity after you train them, right? So that's why we work on a project like this, and so that's sort of the idea behind it. Now, coming to your broader question, and this is a very difficult answer about what this relates to artificial general intelligence. I guess this is philosophical at this point. It's not a computer science question, because you can't define what is AGI, right? Artificial general intelligence. In my perspective, yes. I mean, as part of any sort of general intelligence like us humans we exhibit creativity in some way, right? And so, seeing building models or seeing models are able to express this sort of creativity is I guess, a nice sort of feature that would be nice to have, you know, as part of general intelligence. But in terms of, is this, you know, definitively one critical feature that AGI needs to have? I don't have any answer to that. Like I said, it's a philosophical question. It's not a real science question because you can't really define what AGI is. So that's sort of my somewhat short answer to
it is very difficult to define what the end goal of AGI is.
Exactly.
There's this, like, all the big tech CEOs kind of saying it's coming in 3 years, but I think in my own vision of what AGI is, it kind of needs to like have meaning or emotion that can't be measured. Because when they discuss things like on a human level or compared to, or I guess better than human capability, it kind of feels like to be better than a human, you can't necessarily just be kind of calculations or regurgitating the internet, but you have to somehow think, which is very weird to think about. But it is not very scientific. It's more philosophy and those kind of questions.
So I want to add a little bit on that, what you just said. So if you think, you know, using AI specifically for just, you know, improving our lives in all sorts of different ways, if you're thinking very sort of application driven sort of AI, you don't really always need, you know, AGI or a buzzword or like have emotions in them, etc., etc. I mean, you can build very useful tools without, you know, building a human replica basically. And so in my view, AGI is a nice buzzword to sort of keep sort of like the hype cycle of this AI, right? Because it's a nice word, right? Artificial general intelligence. It's something that sounds really nice, and you know, someone that we all aspire to want to build something. But it's like you say, it's not a concrete goal because you can't really. It depends. If you want to define a concrete goal, then you might realize then AGI is, you only need to build certain parts of what really AGI needs, right? And so then what really is AGI? It's nothing. It's mostly a buzzword. So I don't work in my research thinking I'm contributing to AGI. I think in sort of like, you know, AI startup and AI companies, I mean, because how it works, how the economics work is that they need to get investor confidence and sort of, you know, money and all that, right? Creating that sort of hype is important to them, but not for me. I'm not driven by investor money, right? So I don't think in terms of, you know, AGI research or anything like that.
Yeah, and when you think the hype eventually dies down with AGI, which, well, we never know for now, we don't really know, but what is the next step in research with natural language processing?
Yeah, so there are many different directions, and I guess I'll talk about what I'm interested in, I suppose. What I'm really interested in is sort of reverse engineering. At the moment, at least, I see there's a long way to try to reverse engineer and really understand what these AI models are. So, as you may have heard already, we don't really know why these large language models do the things they do, why they're able to reason the things they do. They're largely a black box system because the analogy I sort of tell people and my wife and, you know, lay people is that we don't write programs and write rules to tell them you should do this and do that. What we do is we do machine learning, which is basically we have a computational models that has ability to learn from data, and we give them the data and we let them learn. So it's kind of like teaching a, you know, 2-year-old language, right? I mean, we tell them, okay, you know, this is how you speak, and they listen to you, and when they say use a wrong verb, we tell them and all that. But in the end, I don't really know in my 5-year-old now, in her little brain, where are the neurons that correspond to what word. I've got no idea, because again, a little toddler is a learning machine, it's a learning thing, right? It takes data, it learns about the data and how to infer patterns and all that, but I don't know internally, you know, what is inside there. And it's the same thing we have with these sort of large language models. When they have made mistakes, when they hallucinate, another big problem, we don't really know why, because, you know, it's all inside the neurons, right? And so I think one of the big things that I'm very interested in, and also a big part of the community, is actually reverse engineering and trying to dissect these models a little bit to understand what is inside these models. And a little bit more concretely, What we're interested to do is, for example, understand how knowledge is stored in, in the big models of neurons that you have, for example. And it turns out it is possible to trace, traces of knowledge, like even like say, Parisian speak French, like let's say knowledge like this, tracing it down to like at the neuron level, what are some specific neurons that are responsible for these things? And to me, this is really important because if we have a better understanding of what these models are doing, how they store knowledge and process knowledge, etc., then we may be able to fix problems like hallucination in a more principled manner rather than a more sort of ad hoc sort of like manner.
Yeah,
if
and
that makes
also
sense.
kind of building on top of that, if we're able to figure out how a model works, would that also have like large impacts on learning and education?
Yeah, of course. I mean, it would help us at least understand how these models arrive in the capability that they have, right? And in terms of the education, it educates us the next generation of models we build, how we can build them in different ways that have say address a particular limitation, etc. So yes, I mean we do this sort of research not just understanding for understanding's sake, but also could have sort of carry forward effect into the next generation of models we build and whatnot. So and of course education for the public and for lay people is that we can now explain why they do things that they do, and when they make mistake, why they make mistakes. So
Yeah, although would it be a little different in terms of like public education? Because with a language model and machine learning models, you're kind of just feeding it a lot of data. It's kind of different from how we think about learning. So like when we think about learning, you think, someone's kind of teaching you something and they teach you once and you're able to replicate it. So would the results or findings from kind of figuring out what actually happens in the black box be different from
absolutely.
public education?
Human learning. So one thing I want to make it very clear is that these computational models learn very differently from human learning. And I don't mean that any sort of like learnings that we learn from how these machine learns translate to how human learn. Definitely, the data, the learning mechanism, they're all completely different. So we wouldn't make that sort of jump. Some people, that there are some research who try to learn from how these machines work and hopefully translate some of the insights we have about how our brains will learn. But I don't want to make that sort of jump. I feel like I'm not doing that to try to understand the human brain in this case because they're just mechanically very different. Yeah.
Yeah, so yeah, it would be very different, and yeah, I guess the process of what learning has been over, I guess, the human lifespan and civilization as a whole has been very different from the architecture of machine learning models, which is like, I guess, a lot of maths, and it's all really a mathematical foundation that changes that. So yeah, I think it's very fun to think about, is there potentially something in these models that could really change what education is all about? But yeah, I think just how it's built.
I think it's the reverse. It's more how we can use how human learn, change how machines learn. And I'll give you examples. One of the things that's very different in terms of how these computational models learn compared to human learning is just the quantity, the amount of data, right? I have a 5-year-old, like the amount of text she's exposed to in picking up language is not in the order of trillions of tokens, right? Whereas these models, what they're exposed to, trillions of tokens, right? Now, but then again, we need to understand also the type of supervision signal we give to these models, and the toddler is very different. What I mean by that is that in training these sort of trillions of tokens, we are doing what we call unsupervised learning, which is getting them to play this really simple word guessing game, right? Where I give you some context, some words in the front, and then we get it to train to predict the next word, basically. I don't get my 5-year-old or 2-year-old to do that, right? Like I don't tell them go read Wikipedia and try to guess the next word, right? Like that's a very sort of crude learning process. That's why it needs to train on lots of data to learn language patterns, right? How human learning is much more data efficient because we give them more explicit supervision. When they start uttering words, if they make a mistake, we tell them explicitly, oh, you shouldn't use this verb here, you should use the other verb instead, or we tell them, oh, this word means X, Y, Z, it's not appropriate in this context. Like you give this very explicit supervision to a toddler when they're learning language. But we don't do this for machine, right? And you might ask, why don't we do this? Well, who's going to do this? You literally just sit with a machine and give explicit supervision for hours and hours. So the problem is that there's no teacher when we are teaching these models, right? That's why we train on lots of data, because there's no teacher. We just use a very crude sort of like game to get them to learn language patterns, and that's why we need lots and lots of data to get them to learn the language pattern. Now, the obvious thing, of course, is how can we, still mimic the human process without this explicit teacher, because no one can sit there for 5 years to teach a machine. How can we still have something like, this human learning without an explicit teacher, but in a more data efficient manner to teach machine? And that would be a very nice thing to aspire to do.
I think I've heard something similar with like teachers and kind of you do something wrong and then they do that, which is I think very related to reinforcement learning.
Yeah.
And I think there's been research done on reinforcement learning in large language models.
Oh yeah, absolutely. So the process how we build this large language model is we do this trillions of tokens of next word guessing game that I told you first. That's only the first part, and then afterwards we would do all sorts of post training. Reinforcement learning is what you mentioned. It's just one part of it, and these sort of post training methods, they don't operate on trillions of tokens. They still use nowadays millions of tokens, but they are doing different type of learning. They're not doing word guessing game. For example, in reinforcement learning, what we do a lot is, for example, get them to learn values. Because a machine model, the model that we want to use is not just a machine that just say things whatever it wants, right? For example, in ChatGPT, you might not want them to say harmful things. You might not want them to give harmful advice, for example. And so to build these sort of human values in there, this sort of reinforcement learning method is very good. And it's really simple. You basically tell them, this is a good sort of response you have, and this is a bad response you shouldn't have, and you have these sort of like a pairwise sort of data to tell them to sort of align them to sort of values that we want them to have more. And there are many other post-training things that we do, like getting them to follow instructions, for example, etc., etc. So all these post-training is what most people would experience nowadays. We don't just use that the pre-trained model that is just on trillions of, because that model can't follow instructions. What you can do with them is that you can give them like 5 words and they'll predict the next word for you, but that's about it, right? But that's not a very useful model. So you do a lot of post-training to get them to be able to chat with you, to follow your instructions, to make sure they have good values, etc.
And this kind of post-training with like reinforcement learning, is that a lot of kind of just sitting there kind of thinking about what do I want this model to do?
Absolutely. That's right. So they would, they would recruit lots of people and then basically get them to either write down the correct response, wrong response, or like get models to generate responses first, and then get humans to rate, oh, this is a good response, that is not a good response. So there's a lot of manual labor there, and that's a more explicit supervision that we're now giving to the language model. Yeah.
And also, I think, kind of relating back to this idea of AGI, there's kind of a lot of manual labor needed in AI. You need a lot of data, you need to label it, all that. I think it kind of, I guess this is a topic that maybe I shouldn't delve into too deep, but the idea with AGI is that eventually you won't need this manual labor, right?
Of course. The manual labor is to kickstart the learning, right? And the idea is that, okay, you do all this manual labor which captures human knowledge basically, or human preference or some way, right? And you get the model to learn it, and hopefully after it learns it, then it's all good now and can do everything that a human can do, and that's the general idea.
Yeah, and then kind of it will then be able to create its own models, which is
we're not quite there yet, yeah. But the idea, well, in sort of science fiction or sort of like the general fiction, is the idea is that a machine, once smart enough, would be able to design the next machine, right? And because we can design machines already, and if they understand how we design machine, capture all that knowledge, then they can design the next better machine. And of course, you're gonna have this loop where they're gonna design better and better machines, and eventually singularity or whatever can happen.
Yeah, so I think this process of generating its own machine, how would an AI model build another AI model? Because it seems so weird, especially with the necessary for data.
Yeah,
So I
yeah.
think,
So again, it depends on whether they generalize, right? Because you can say, for example, so when I say build, let's not think about the mechanical bit, like actually going to a factory and putting things together. Let's just think about building in terms of coming with a conceptual idea of the next machine. In that bit, you just need to technically you can generate like a schema or a piece of text that describe how you build the next machine. And so you don't need physical robotics and all that. So let's focus on that bit first, because the robotics bit, technically after you create the idea, you can get humans to build the next machine anyway, right? But so how can they even like come up with the next design? Well, if you think about it, if you get a very smart large language model who already understand instructions, human language and all that, you get them read all the research papers about large language models, how we build large language models, right? If they have creativity, and this is an if, we don't know yet, if they exhibit creativity, they might be able to come up with a new idea to build the next generation of large language model. Because all our knowledge of how we build large language models are captured in these research papers. So if they can digest it, if they exhibit creativity, they could propose the next, like architecture or whatever. So that's how you're gonna build these things.
yeah, there's kind of that large talk of, especially with text generation, that there needs to be a new paradigm in order to facilitate like these models that can build themselves, which is kind of hard to think about, because with how these models are built with like lots of data, and then you use certain mathematical formulas to kind of link together words and so on. It seems like a shift in thinking would be very hard to do.
Well, it's not impossible. I mean, because remember I spoke that previously there was no teacher to build the first generation large language model, and so you have to do all this trillion of token. Maybe one crazy, and this is not science anymore. This is all just speculation at this point. Okay, one crazy idea could be that maybe they could serve as the first teacher for the next generation of language model, right? Where you're not going to train on web data anymore, because we've already used all the web data basically, right? And any new web data you're gonna get is probably machine generated data, which you don't want. So it could be that the next generation is not gonna be trained on just this sort of very crude next word prediction objective, but more like a child where you have an explicit teacher teaching them, giving an explicit signal. Maybe, I don't know. But this is all speculation. I need to say this is not like science. This is not even something I research or think about. I'm just giving you speculations.
Yeah, but I think it's very fun to think about, especially with how there's like a lot of news on AI about AGI is in three years, this many years, and it's like, what are they trying to get at with that? Which is very fun to think about. And I think how's our time going? Because I think it's all outside.
22 minutes.
Is that well good? I think another thing I wanted to discuss especially with AI and creativity, was that because I think they are actually able to really, I guess, be creative in a sense, especially, I guess, with image generation, there's like Mid-Journey, and there's kind of this big news topic about Mid-Journey creating an art piece that won an award. If they're able to be more creative, does that kind of force us as humans to also become more creative?
I mean, it depends. It really depends on what we're talking. But before we jump into that, I just want to again probe this creative question. Like, are they creative, right? No one knows. Like, we don't know yet. And I wouldn't say because Midjourney created something that won award that they're creative, because we never know. Because we never look into the database of all existing painting, whether there's like two images that are very similar to what it created, and actually it was just mixing these two painting together, right? We never did that verification, because in order to really validate creativity, we need to check against this whole database of painting that has seen, and how similar it is to any of these existing things. If they're not similar to anything that has been trained on, then you can claim, yes, they are creative, right? But we don't know that. It is very possible every poetry you see, every image they generate, are actually drawn from their training data in some way, or blending some stuff in some way, right? But we we don't know. We haven't validated yet. So I wouldn't use like award as a way to validate their creativity. Now, I want to highlight this because there are areas that we can see they don't have creativity or generalize. The creativity is the same problem as generalization. Can they generalize to new sort of like patterns, right? For example, even with large language model, this may shock you. They do very well, say multiply 2 digits together or add 2 digits together, okay? But you will find that as you increase the number of digits for the first term and the second term, like 1 plus 1, single digit, 100% accuracy. As you increase the number of digits, like say 2 digits plus 3 digits, and you keep increasing, you will find that the performance sort of like decrease as you increase the number of digits. That's not how human behaves, because you have learned the general principle. Yes, it's very tedious to do 10 digits multiplication, but we can still do it, right? But you'll find that these AI models decrease over time, like over as the digit increase. So then the question that we all ask is, do they really know how to do multiplication? Or maybe they just seen all the possible, smaller digit multiplication or addition in the data, because you have trillions of tokens, right? Maybe has seen like, 101 times 353 in some slice of the training data and remembered it. So we don't really know. So I think all this is building a cautionary sort of like observation for us that we don't truly know whether these models generalize yet, or what type of problems they generalize to, or whether they have creativity. And so let's not assume they have creativity. To answer your question, like, does that mean we humans need to become more creative as they become more creative? I guess it kind of, I don't have an answer for it, but I'll use chess as an example. It's a good example because it's not just chess. Chess already has an AI that beats human all the time, okay? And they're very creative. They play differently, okay? And do we watch chess AI play with each other? No one does that, right? Because part of the reason why we find it entertaining to watch people play chess is the human element in there, the personality, the character, the human spirit, etc. Right? So it does make chess players, like practice against this AI to become more creative, but it doesn't mean that just because we have AI chess players it would replace human players, because it's not about performance basically, and this applies to all sorts of sports scenario if you want to imagine. So, but again, it depends on what scenario, what sort of domain you're talking. Here we're talking sort of sports competitive matches. I feel like you can probably build AI to do many different sports and it's going to be better than human, but they're not really going to replace human in any way, because we want the human element in there. But there are definitely other areas where I don't know if we talk about poetry writing, right? I haven't thought about it myself. Would we write really good poetry written by some AI? I mean, I don't know. I mean, I personally would feel not super interesting, because like it's not from a person, not from their lived experience, right? But maybe people might. And same with like paintings and all that, right? Would you just want to look at beautiful painting created by AI? Again, like, it's not just a painting. Like, to me, when you like a painting, you look at the history of the painter, the artist. There's a human experience behind the painting, expressing their views, their emotions, all that, right? It feels hollow when it's just a generated AI painting, for example. But again, I'm not an expert. This is just my very subjective view.
Yeah, because I think with art and AI, it is very subjective. And I think one of the things you mentioned was like, do you really want to see something created by an AI? And I was thinking, at like what point is it impressive for an AI to create something? So I guess it's impressive that AI can beat all the top chess players, and maybe it's impressive that AI can create a very good looking image. But at like what point would it be considered impressive? Because in the case of poetry, I think with your paper on DeepSphere, it was able to generate good poetry that most people couldn't tell the difference between. But when you presented it to an English professor, they were kind of easily able to tell it. So would the point at which it is impressive be that it can trick someone who's very, very educated about the topic?
I mean, impressive is again very subjective, but I guess if we want to measure like performance, like at what point would we say the generator, the poetry generator, is performing at a level similar to human, let's say for example, then I would believe yes. Then if they they generate poems that even an English literature professor couldn't tell apart, then I would say, I wouldn't say impressive, I would just say they have reached a performance where they generate poetries that just like human poetry basically. But again, we need to remember, just because they do that really well doesn't mean they're creative yet, right? Because remember my point, they could be plagiarizing from the existing training data. We didn't check that. We don't really know. So yeah, that's a two different thing. Like whether they create poetry that is like very good and can fool people, but whether they still exhibit creativity is still yet another question. Yeah.
Yeah, and it would be very hard to determine if there actually is creativity.
Easy if you work with small data. Like when we were training them on 3,000 poetry, it's not too hard, right? We just need to look at the existing 3,000 poetry, is it close to any of it, any sonnets, and then we can test it, and we did. Of course, we realized it was generating new things, so that's why we know it's creative. But when you work with large scale, like large language model trained with trillions of tokens, where we don't even have access to the data, we don't even know what the data is trained on, then it's not possible.
Yeah, so then it becomes very hard to try and search for that poem in, well, I guess if it was a large poem generated, to search for that in there. I think.
Yeah, and commercial companies aren't going to do that, because that doesn't help them get money, right? So they have no incentive to understand creativity, like whether they're creative or not.
Yeah, so they would just try and create something that's fulfilling what people want.
Yes.
What people kind of are afraid of, potentially, kind of feeding into the narrative of what AI is really good and so on.
Yes.
But yeah, I guess the sense of creativity. Yeah, I guess in terms of large language models, it would be hard. But I guess it's a very philosophical thought, but how would you determine that generated text would be creative? Because it seems like I believe there's like 9 billion humans on planet Earth, that any sequence of words has been created before.
Yeah.
So I guess how would you determine that a large language model is creative if everything has been generated?
No, you underestimate the sparsity or the scale of combinatorial sort of like factors. If you have 50,000 words in your vocabulary, unique words in your vocabulary, even just a 50-word sentence would have so many combinations that they would not be captured in a trillion corpus.
And kind of over, I think, I actually don't know how long language has been created, but is it possible that throughout all of human civilization, all language, that we still haven't really, or we haven't created enough text to determine if, I guess, kind of losing, when we think about this thought, that what we've all created, I guess, is still different from what AI can generate.
Absolutely. So remember what I said about in the 50-word sentence. There's so many combinations, even with the 50,000 vocabulary that you have, you can generate so many combinations of 50-word, say, paragraph, that it's not captured by even 1 trillion training corpus, right? So what that means is that there is still lots of space you can create very unique. I mean, not completely unique, of course, but the sequence, the 50-word sequence, can still be very new ideas. So yes, you absolutely can. Yeah. Because the space when you put all these like 50K word and you have 50-word sequence is so huge that no amount of like even the web data wouldn't be able to cover it. So yeah, you can still come up with a new idea. I mean, we're talk, if we want to be a bit more grounded, we can talk about things like, say, a novel or whatever, right? You can still come up with new narrative. Yes, absolutely. Yeah. And even word combinations. Just the other day we were chatting, like, what is the what is there any sort of a like relationship between the letters and prejudice and perjury, for example, just 2 words. And it turns out, even on the web, there are no articles that link perjury and letters together in the same document. And the web is huge, right? Yeah. And so there are so many concepts that, you know, the whole web is not going to cover all possible combinations. Yeah.
Yeah, so there's kind of still a gap within the data that we use to train AI. but
For sure,
yeah,
I wouldn't say it's a gap. I think it just shows the amount of flexibility that we have in our language to create expressions. There is so much flexibility that even, you know, tons of data, the whole web is not going to capture all the possible combinations of concepts. Yeah.
And also, I'll kind of think about a different topic for now, but with regards to 1 trillion words, I think thinking, I don't know how to convert that into actual storage, but I believe that how would you actually deal with, if we say we had 1 trillion words, how would you feed that into a large language model? Because it's so much data.
Yeah, no. So 1 trillion would be, I mean, we work with sort of these sort of data sets before. You're talking, you know, hundreds of terabytes. So it's not infinite. Like, you can certainly have enough storage to store them. These models, even though they're trained on like trillion corpus, right? It doesn't mean they need to see everything in one shot, right? Because what they have in the input is that there's input limit to them, like maybe 1,000 tokens, or nowadays 1 million tokens, and that's a limit. So what that means is that if it's 1,000 tokens, they can only see 1,000 tokens in the input, and you can feed into it, and then they predict the next word. So what you do, even if you have 1 trillion token, is that you slice them up into, say, 1,000 length sort of like sequences, and then, you know, let them see 1,000 length sort of sequence one at a time. So you would be able to process them like that way.
Yeah, that is true. Yeah. So you would just kind of split everything up and then feed it eventually.
Yeah.
Yeah, which would make sense. And I think what was it? Sorry, I kind of lost my train. What was the last topic we were discussing before? I think it was.
I don't remember.
With,
Was that something we want to come back to?
I think I did want to come back to like because it's very weird to think about language, and like it all relates back to not really computer science, but it relates mostly back to language and linguistics. And I think one of the questions I wanted to ask was, when you're building such models, or is there more focus on linguistics and literature than there is a focus on computer science?
Now that's where, you know, I talk about the evolution of the field itself. When the field started, it's not really called natural language processing. It has another name called computational linguistics. Nowadays, they kind of mean the same thing, but when they started, it's slightly different focus. Computational linguistics is about trying to use computational models to understand, say, linguistic theories. So we build models not to say for an application, but to check whether a particular linguistic theory's assumption are correct or not, for example. And that's sort of, you know, what a lot of computational linguistics works are about. Now, when the field started at computational linguistics, NLP started in the 1950s and all that, there are a lot of sort of linguistic theories being built into the models that we do. Inspired, either we directly draw in, you know, the assumptions they have, the axioms or whatever. And what you'll see, even though there's no chart I can show you, is that over time, if you look at these sort of research area, the amount of linguistic theories that we import into building these computational models is sort of like basically going down. And if they talk about large language models themselves, there is no linguistics theories that we put into the models themselves. You know, there's nothing. The reason why for that is because a lot of these linguistic theories, they are theories that are not perfect. There's no perfect theory. It's not like physics where you can, well, even in physics, it doesn't fully explain all the phenomena, right? And so what you find is that as you incorporate these sort of linguistic theories, they might help improve certain areas or certain parts of the language pattern and whatnot, but they don't always work in all sorts of areas. And so, you know, people figure that it's actually probably easier that we just build a computational models without having this baggage, basically. If you think about building a plane, let's say for example, we didn't try to build a plane to follow how birds fly, right? In fact, what we do is that we learn the underlying sort of physics behind, you know, aerodynamics, etc., and then we build a plane that flies but doesn't work like a bird at all. It's very similar how we build these large language models. We have some inspiration, we understand some theories about how language works and all that, but beyond that, we build these things basically using mostly math and without any sort of like linguistics theory sort of imported behind them. So not so much. Yeah.
And I believe the main idea was, well, currently with generative AI is the transforming the attention model. So linking of words. How has that changed in the last 5 years? Because I believe in your DSCubed paper in 2018, you also looked at preceding contexts. So that was, I believe, kind of an attention mechanism?
Yeah, there is attention mechanism, but very different to the transformer-based attention mechanism that we use nowadays, which drives all these large language models. There has been sort of several architectural leap in the past sort of 10 years or so. We started simple things like feed-forward networks, recurrent networks, and then eventually we now have these what we call transformer networks. Attention exists already before transformer, but exactly how you compute attention is a little bit different. Transformer has its own very different way of computing attention. But attention is, generally speaking, something drawn from psychology, right? Like how when you read a piece of text, you will notice that your eye will focus in some words more than the others. That's a form of attention. Transformer models do something like that, where they can attend to all these different words and give different weights to different words, how they attend to. So you can sort of think that it's in a way not dissimilar to how humans would have different attention to different words when you read a paragraph. But again, that's a very sort of loose inspiration. The mechanism, how we exactly compute those attention weights and all that is completely different how humans would compute. In fact, I don't even know how humans compute it. But yeah, so it's just a loose sort of connection that you can see there. But yeah.
And that's how like linguistics kind of influences.
No, not so much. That's more psychology than linguistics, actually. Yeah.
Yeah, so it's really kind of a lot of fields coming together.
Yeah, for sure. I mean, you're working in a field that tries to build, that basically has a bit of machine learning, AI, has a bit of linguistics, has a bit of psychology, culture, that basically a fairly interdisciplinary field. Although, as we move more into LLM, large language models, it's more and more just computer science.
It's more field computation. And probably just the last question, which I kind of got inspired by the computer file videos, was what is your favorite programming language?
My favorite programming language is actually Python now. But I didn't grow up using Python a lot. I grew up using C a lot. But after I learned Python, I think it's in the right abstraction level that I think it's great to use. And also because if you do NLP, Python is really the main language, because a lot of the NLP toolkits are all in for Python. So Python would be my favorite language. Yeah.
All right, that's great to hear. All right, so yeah, thank you for joining us for this episode, and
Hopefully.
it's really great to listen to your insights.